He's also tired of that.
Wow, you've only been here for like...
We haven't even overlapped till today. This is our first day together.
All right. We're kicking off the colloquium series for this semester with our first talk by Professor Simeon. He got his PhD in 2011 from Cambridge, where he was working with Martin Hingel and Haramia Pyrus. Is that correct? No? Yes.
Ish.
Then he moved on to the IAS, and then to Carnegie Mellon, where he was a Williams Fellow, and then an Einstein Fellow at Johns Hopkins. And just this year, I believe, he has become one of our local colleagues, joining the faculty of UC Riverside. Simeon works on all kinds of problems in numerical cosmology and galaxy formation, especially the circumgalactic medium, the intergalactic medium, and topics in dark matter like primordial black holes. And so, looking forward to what you have to say. Welcome, and thanks for coming.
All right, thank you very much for having me. Right, so, okay, there we go. Okay, so so the point of this slide is firstly to note that I am indeed kind of close. So, you know, if you want me for anything, I'm right there. Well, within reason. The other, this is a slightly odd talk. The reason this is a slightly odd talk is that normally nowadays I get invited places to give talks about primordial black holes. And you didn't ask me to give a talk about primordial black holes, which I'm quite glad about because I'm at this point a little tired of talking about that. So I'm going to talk about something else. What I'm going to talk about is a bunch of things that I did about the same time as the PBH stuff, which actually took longer than the PBH paper to write, but which I never really got a chance to talk about. So this is going to be a collection of slightly disparate topics that I never got a chance to talk about, and so I'm using the opportunity of you sitting here to tell you about it. Okay. So I'm going to first talk about the broad trend of this is some stuff I've done using hydrodynamic simulations to match observations of neutral hydrogen, mostly in the IgM or the CGM. So all of this is going to be hydrogen. There was originally something in metals, but I took it out. First, we're going to talk about Lyman-alpha emitters. Then I'm going to talk about the low redshift Lyman-alpha forest, which is particularly relevant. Is Juna here or no? Okay. Well, this is based on some work that Juna did a few years ago. And finally, I'm going to talk about detecting damped Lyman-alpha systems in SDSS spectra with machine learning, which is something I did more recently, which is quite a lot of fun. Okay. So first, these things. So. This is work with Max Gronke, who's now in UCSB. The way this happened was that he showed up at Johns Hopkins one day in my office and said, "Hey, let's write a paper together." So I said, "Okay." He was I can't remember what he was doing in Johns Hopkins. He was in Zurich or something at the time. This is an observation around 2014 in narrowband Muse imaging. Of Lyman-alpha emission around a radio-quiet quasar, which is this thing marked with a secondary object, which might be another quasar marked in B. And the reason that these were interesting is firstly that this is a very large amount of Lyman-alpha emissivities. This is 2 times 10 to the 44 ergs per second being emitted here. And secondly, it's it's spatially extended. It has a 460 proper kiloparsec extent to Redshift 2. So this was a little strange. You know, this was a Nature paper because this was the largest such object seen at the time. Since then, he's used a similar technique to observe a whole bunch of other quasars, and he's seen lots of these. So they're almost ubiquitous. This one, I think, is still the largest. It makes sense, kind of, that the first one to be observed would be the largest, right? Because the largest one is going to be the easiest to detect will be the largest, so it makes sense it was the first one detected. Where he got probably a little bit lucky was that this was actually the first one he looked at. So, you know, that was maybe a bit fortuitous. Okay, so when he saw this, he ran it through a hydro simulation. This was a zoom simulation of a single large halo, resolved quite highly, using, I think, a grid code. And he found that it didn't really match. He found that in order to get enough luminosity to match the observations, in order to get a large enough halo, he had to introduce a lot of extra small-scale clumping into the gas around the galaxy. So the reason you need to do this is that the Lyman-alpha luminosity is proportional to the density squared. So you can boost it by just boosting the small-scale density by adding lots of little tiny clumps all around the gas. So the idea here is that it clumps on scales that are unresolved by the simulation. Okay, and this was what he said was necessary. So this represented a challenge for galaxy formation models. So I said, okay, this is interesting. Right, a zoom simulation, but I haven't have a larger hydro simulation. So what does this look like in Illustris, which is the simulation I was working on? So what I did was I took 50 halos from a cosmological simulation now. So instead of a zoom simulation with one halo, we have a cosmological simulation with a whole bunch of things resolved. We selected things with the quasar host mass. We used 50 because that's how many there happen to be in this box of Redshift 2. All these halos have a mass of 10 to the 12.5 M-sun, so that's like the rough average mass of a quasar host halo from bias measurements. And we took the gas distribution around the halo and we post-processed it with a radius transfer code to make Lyman-alpha emission maps. So this is reasonably plausible. We also have a dust absorption model, which is based on the metallicity of the gas, and you make some model for the dust column. This is also plausible, probably has some large uncertainty to it. And we didn't use clumping. So we just took the gas distribution straight from the simulation. And so this was the first thing we were going to do. And we were going to, see what this got, and then see how much clumping we had to do to get the right answer. I should mention what Illustris is. So Illustris is a cosmological hydrodynamic simulation circa about 2014. It was state-of-the-art then. It has self-consistent models for gravity, gas, cooling, and metal enrichment. This is one of the propaganda pictures. This is dark matter on the left and gas on the right. And these things in the middle are stellar halos. And you can see the dark matter clumping more than the gas because of pressure smoothing. It also includes models for AGN feedback and for supernovae feedback, which are going to prove, it's going to prove to be important that both of these things are included. In common with every other galactic hydrodynamic simulation, these models are tuned. These models are not rigorous, consistent models. These are ad hoc, effective models. We've picked the parameters to match the stellar mass function and to suppress star formation the right amount. So this suppresses star formation in particular by heating gas and by moving it out of galactic halos. So there is going to be a lot less gas in the central regions of halos, a lot lower density, and a lot more gas in the outskirts of halos. Good. Okay, so if you want to make Lyman-alpha emission maps, you not only need to know how much gas there is, you also need to know where the photons come from. We had two models for this. We had a model of photons coming from an AGN. So we said, okay, let's say there's a whole bunch of emitting region, ionized regions around the black holes. Every time there's a black hole particle in the simulation, a region around that will be considered ionized. The radius of ionization we had as a free parameter. We also said that every time there's a star-forming region, they will emit photons and they will ionize their immediate particles. And that particle will emit in Lyman-alpha. So this free parameter now is the fraction of the star-forming particle that is ionized. And the nice thing about this is that it doesn't, we have a free parameter for each one of these and they don't matter. The purpose of this slide is to convince you that you shouldn't mind too much about the free parameters of this model because it saturates. And the reason it saturates is that there's only so much gas, and it is the gas that emits in the Lyman-alpha. It is the ionized gas that emits in Lyman-alpha, so if you have more photons, you are not limited by your photon count, you're limited by your gas. Okay? And the gas is self-consistent. So what we did was we picked a value for both of these, a fiducial value which was high enough that it was saturated. And what do we get? Behold, we get, so this is an example of one of my 50 halos. This is a reasonably typical halo that I picked. We get these big blobs that have an extent of about 300 kiloparsecs. So they're reasonably about the same size. They have luminosities of 10 to the 43 ergs per second, which is, within the range. It's an order of magnitude lower than Sebastiano's halo, than the Cantalupo halo, but it's within the range. It's close enough. So this is something we didn't have to do anything to get. All I did was I took a standard simulation, which has not been tuned to do this, and I post-processed it to get something that looked like the observations. And behold, I get something that is reasonably close to it.
Well, I'm a little confused because
Yeah.
at the beginning you were saying you really would need a large number of these things, and that's not in this simulation.
That is correct. Right. So this was not what we were expecting. We were expecting to have to monkey around with it. We were expecting to do this as a first check, show that it didn't work, and then monkey around with simulation, and write a paper that said this is how much we have to monkey around with simulation to get the right answer. And when we did this, we found that we did in fact get the right answer, and we were kind of confused. One thing to note about this: the stellar model where I have photons coming from stars and the AGN model, they look basically the same. Like by eye, I can barely see the difference. Maybe there's more of a glow in the central regions for the stars than for the AGN, but it's pretty close. And this is in some sense unfortunate because it means you can't use these kinds of observations to tell whether the source of Lyman-alpha emission is stars or is black holes. But it's also nice for a theorist because it means I don't have to care. The thing that does make a lot of difference is the dust model. So the dust extinction based on metallicity is reducing the luminosity of these things by an order of magnitude. So this is, I guess this is a common feature of many astronomical observations, that dust is important and that you don't really understand it. So we had statistics. We weren't just a zoom halo, we had statistics. These are all the 50 odd halos in our simulation. The star is the Cantalupo et al. 2014 halo. The pentagon is the second detection they made. And these squares are a statistical survey that they made later. Each of these kind of bars is a halo in the simulations. This is the luminosity on the horizontal axis. This is the maximal extent. So that's, just to go back and remind you, that's this arrow here. So this arrow marks the largest width along the halo, along the emitting nebula. The error bars on each of these guys represent viewing angles. So depending on which, in the simulation, you can choose which angle you're viewing the halo at. Depending on which angle it is, because the halos are not spherical, you either get a much longer blob or a much smaller blob, just because they're elliptical. And this is what we have.
Does that not also affect the luminosity?
It doesn't, because it's the integrated luminosity, right? There's no
Okay, so there's no scattering.
there's no redshifting along the halo, right? So the integrated luminosity is roughly the same because it gets scattered once and then it comes towards you.
I mean, it must change a little bit because of the dust distribution. But
Yeah, I don't think we really model that, actually. I think that's I think the dust distribution is done off of the total metallicity of the halo. So the dust absorption is assumed to be uniform, and that's why that doesn't make a huge difference.
So I assume there must be a diagonal line here for some surface brightness detection threshold for the observational lines.
Yeah, right.
So does that just get rid of most of the ones in the upper left, and so it makes it mean to keep it home? Or is it not quite?
I see. You're asking whether these guys would ever be detected because the luminosity would be spread out wide enough. Yeah, that's a good question. I haven't.
And even the ones that are at say 10 to the 44 that have 600, 500, 400 kiloparsecs, because you don't see those yet. Maybe they exist, and again, we can't detect those yet either. It's not just the ones in the upper left completely.
That's a good question. My intuition for this was that the width of, especially for these very wide ones, they're not going to look like blobs, right? Because the variance depending on viewing angle is so large, they're going to be very much non-spherical. So if you're looking for a round thing, you're just not going to see them.
But some fraction of the time they will be sort of correlate along the line of said enough that they would still look round.
Yeah.
Right? I get it. There's a geometry and surface brightness detection threshold operating this diagram, but you can wait until later because you have a whole talk to do. So
also, they're not predicting the abundance.
that's what I was wondering about.
Well,
So-
they've got 50 from the simulation. That's
Yeah.
right there is a space density.
So how does that compare to the things that are down on the ASCII?
I would absolutely not trust this calculation far enough to say that with any degree of confidence. I think it's legitimate to say that they're, okay, well, the conclusion of this bit of the talk is that I think there might actually be slightly more of these in the simulations than there are observations. So we've reversed originally we thought that there were fewer of these in the simulations than you observe, and we seem to have reversed it because now we get more. So that's fun. But whether, how significant this is, because we're being moved down by an order of magnitude by dust extinction, I'm not sure I trust, this factor of 2 here to any huge degree. It does look like these things are ubiquitous, that both in the simulations and in the observations, you are getting a lot of these objects, these emission objects around halos. So that's a reassuring thing. A slightly less reassuring thing, you might hope that there are some correlations here. They do not look like there are any real correlations here. Like, this just looks like a mess to me. There's no correlation between the maximum extent between the maximum extent of the luminosity, and there's no real correlation between the mass of, this is the mass of the host halo, and luminosity and maximum extent, which is unfortunate. One thing, you can change your metrics slightly. So instead of looking at the maximum extent, you can look at the average radius of this. And this reduces the scatter based on viewing angle, and it makes there's a strong correlation now between the luminosity and the average radius. So this is as you would expect, that brighter objects are indeed more extended. This makes sense because, if there are more halos, if there are more photons in the middle, there are going to be more photons in the outskirts. This is a self-similar brightness profile. I think I removed that slide, but it actually is a self-similar brightness profile. The power law with which the brightness emission of the Lyman-alpha emitter drops off is more or less constant, irrespective of the halo. And that's matched in both the simulations and the observations. So there is this correlation between average radius and luminosity, which suggests that if you're doing this as an observer, this is the metric that you should use rather than the maximum extent, which is extremely noisy. Note there is still some variance based on viewing angle, because the average radius is averaged over a 2D radius projected, and the viewing angle depends on your 3D orientation. You asked why it was that I get this right and the earlier halos didn't. And there are 2 reasons, and both of these reasons are important. The first reason is that he had bad luck, right? He only simulated 1 halo. Look at all these halos. Maybe he simulated this one. You can't beat bad luck. There's a huge variance here, and we really need this whole statistical sample to get it right. And arguably, we need even more halos to get this properly nailed down. The second thing is that he had no AGM feedback. So I told you right at the beginning that the AGM feedback is suppressing star formation by blowing gas right out of the halo. This is important. This substantially increases the covering fraction of neutral gas. So you're never, ever going to get these radius numbers to be this high unless you're blowing a lot of gas out of the halo. So one interpretation of this, the fact that this is somewhat higher than the observations, just a little bit, is that you are blowing too much gas out of the halo. In other words, that the illustrious AGM feedback model is a little bit too aggressive, which is something that we know already. Okay.
So have you compared this to like the quasars absorption line work?
I haven't done that. That would be, those, I didn't have a large enough sample for some reason in Illustris to do that. I tried it, and I think it's either because their redshift distribution, they're slightly higher redshift, or it's because the quasars probing quasars tend to be at a higher transverse distance from the host, and I didn't have a large enough box. I am thinking of trying that with TNG, because that really was just a sampling issue, that Illustris just wasn't a big enough box to do that reasonably. And they have a bigger box now, so we can do that. But that would be a fun thing to do. Okay. The last thing that I want to note before I finish this bit is that the color here is the mass of the halo. You might expect the mass of the halo to be well correlated with Lyman-alpha luminosity, right? If the halo is larger, there's more gas around it, so there should be more photons, so it should be more luminous. There should be a larger radius of these things, and this is not the case. The most, sorry? That's true, right? So there's more dust extinction. That probably gets folded into here too. It probably would look better if I looked at the intrinsic luminosity. That's true. But this is not the case. One reason this is the case, right, the dust. Another reason this is the case is that the amount of gas around the halo is being set by the AGM feedback. The AGM feedback is bursty. So in some sense, what we're seeing here is the time since the last time AGM feedback went off and the effects of AGM feedback reached the CGM. So we shouldn't really expect a strong correlation between the amount of neutral gas that is emitting the amount of gas that is emitting in this way, that is at the right temperature and has the right properties, and its radius around the halo and the halo mass necessarily. Yeah.
So would you expect line width to simply be the better third axis?
I would love line width to be the third better axis, but I couldn't get a reasonable measurement of line width out of the simulation because we don't resolve the physics of the line width. We have a plot in the paper where we look at microphysical models from the stars and from the AGN, and the line width looks completely different. And we were exceptionally annoyed by this, but that's what that's what can you do? Okay, any questions on this before I go on to the next one? Yeah, and those look very different from the Lyman-alpha profiles for the Lyman-alpha emitters. We match in the simulations the Lyman-alpha profiles for the Lyman-alpha emitters, and we don't match. If I'm really lucky, I left this as a backup slide somewhere. I don't think I did. That was silly of me. Okay, well, if I'm really, really lucky, I have this somewhere. Hang on.
I want to totally derail.
You know, what's the... Yeah, I do. Okay. Okay, right. This is the Lyman-alpha emission profile for these objects. So each of these lines is a halo in the simulations. The other things are stacks. The red line is the red and orange line are stacked from Lyman-alpha emitters. This is only one object, which happens to be the most massive. And you can see we agree well with that one, and we don't agree with the overall stack, which suggests, again, that we have too much now. And these guys are the Lyman break galaxies. So the Lyman break galaxy stack is substantially lower and substantially less steep than the Lyman-alpha emitter stack. So that suggests to me that they are actually a different population. My guess is that one plausible explanation for this is that these guys all have quasars in or near them, and that it is actually the quasars that's causing the Lyman-alpha emission. I don't want to go on record as saying that that's definitely the case, but that's one plausible explanation. Okay. I'll leave that open in case you want to ask something more. Okay, yeah, so much for Lyman-alpha emitters. So that was a plausible observational problem that we matched by adding AGM feedback to the simulation. And the moral of this story is that if you add enough AGM feedback to suppress star formation sufficiently, you kind of match the amount of neutral gas around the halo almost automatically. So there's something physical that's happening here. Like the suppression of star formation by removal of neutral gas seems to be the right thing to do. The next thing I want to talk about, the low redshift Lyman-alpha forest. So these are weak neutral hydrogen absorbers, as seen by the Hubble Space Telescope. They have to be seen with Hubble because there's an atmospheric cutoff at redshift less than 2, as I think everyone here knows that. You can get a column density distribution from Hubble, a histogram of the absorbers in weird observer units, which you'll probably consider extremely natural observer units. But speaking as a theorist, I consider them a little strange. This is what you get. So this is a stack, a column density distribution of neutral hydrogen in the Lyman-alpha forest from HST with a column density between 12.5 and about 14. So this is a hydrogen column density 10 to the 13 atoms per cubic centimeter per square centimeter. This is a plot from Juna Kollmeyer's paper in 2014. So she ran a simulation with a standard model for the ultraviolet background. And she discovered that with the best model of the ultraviolet background we have today, which is this one, Hartmann-Dow 2012, you get far too much neutral hydrogen in this model to explain the observations. These are mostly photoionized, so they're maybe 80% photoionized and maybe 20% collisionally ionized. So if you want to have less neutral hydrogen, you dial up the amount of photons. More photons mean more ionization of the hydrogen, less neutral hydrogen, better agreement with the observations. So the paper she wrote was called the Photon Onto-Production Crisis, and the argument is that there are too few photons in the models at redshift 0, so you need to have a whole bunch of other photons coming from somewhere. Where do they come from? Okay. So again, I say, okay, I happen to have this big simulation. Oh, let's see, whether this agrees. I happen to have this undergrad who is now at Northwestern working with me at the time. So we look at it. And again, we get pretty good agreement. So illustrious matches somewhat better. The factor of 5 or 10 offset is gone again. This blue line is illustrious. The black line is Juna's results here, and the pink is the observational detections. And this is a factor of 2 to 3 reduction. So your next question is, why is this the case? And there are 2 reasons. So 2 reasons. Why? One reason is we do, in fact, have more photons. So this is the boring reason. We are using, instead of the Hartmann-Dow 2012 background, we're using the Fauché-Giguère 2009 background. What is the difference between them? The Hartmann-Dow ultraviolet background assumes that all the ultraviolet photons in the universe come from quasars. The Fauché-Giguère background assumes that some small fraction of them comes from a Lyman-alpha escape fraction of galaxies. So this means that because quasars peak at redshift 2 and then drop off very sharply, by redshift 0, you get substantially more ultraviolet photons if you assume that the photons are coming from galaxies than if they come from quasars. And this, I think, is a factor of maybe 1.5 or something. This is about half of the difference. So you see here this dotted line. I've run it using the same ultraviolet background model that Kollmeyer used, and I get something that's closer to what she got, but not quite the same.
Even if the emissivity has to be, I don't know, it's probably very low.
It's very low.
But you still get more because of it.
Yeah. So if you look at the number of photons there are in these UV models, by very low redshift, there are actually very few UV photons just in general. So even a small UV emissivity from galaxies makes a big difference.
So what's a typical number?
Like 5%, I think. Maybe 2.5 to 5.
That's a large scale. At 0 redshift, essentially.
I think that's right. Somewhere between 2.5% and 5%. Yeah. Is that so? Well, okay. So.
That's people are struggling at. It's 1 to 2%. That's why it's so far from what you need to redshift 6 and 7 for the organization.
Yeah, so for the large galaxy populations, that's true, although they have found some a handful of galaxies that leak a large fraction of their photons, which is kind of potentially interesting.
But a large fraction, maybe 5 or 10%, right?
No, much higher, but for single galaxies.
Right.
Okay.
So you need to have some way of getting photons from galaxies for this UVB to work. So this is, like I said, this is the boring reason, right? And it's kind of boring precisely because we can argue all day about what the emissivity of galaxies is, and really we don't know. It's legitimate to say, okay, maybe I believe Hartmann-Dow, maybe this is a better thing to do. The point of this plot really is to say that there's more uncertainty in the ultraviolet background amplitude than you might naively think. The other reason, which is more interesting, is that we had AGM feedback again. So here, what I've done, this is the green line again is illustrious. These other lines are illustrious with some of the feedback switched off. So I have two plots here. One has no feedback whatsoever. One has only supernova feedback but no AGN. And one has AGN feedback and supernova feedback. There is no model with only AGN feedback because the way illustrious is set up, if you turn off supernova feedback and leave AGN feedback on, everything goes very, very wrong. The AGN feedback is driven by the falling of neutral gas into the black hole. And if you have no supernova feedback, you get a lot of neutral gas falling into the black hole. Whenever the AGN goes off, the galaxy gets ripped into tiny pieces. It's very beautiful to look at. It doesn't bear a lot of resemblance to what you would see in reality. The point of this is that the stellar feedback here is not making any difference, really. The AGN feedback is making a huge difference. So all the residual changes between our results and Juno's results that are not accounted for by the ultraviolet background are accounted for by adding this AGN feedback in here. You might be concerned by this. The reason you might be concerned by this is that you know that this is the Lyman-alpha forest. And what you know about the Lyman-alpha forest is that it comes from the intergalactic medium. The intergalactic medium is kind of defined to be stuff which is about the mean density of the universe, maybe a factor of a few higher than the mean density of the universe. And it is not affected by galactic physics, right? This is why we care about it. This is why we as cosmologists are interested, because it is not affected by AGN feedback. And you don't have to worry about the fact you don't understand galaxies very well. But this is at redshift 2. If you go down to lower redshift, because the mean density of the universe decreases, you are probing higher and higher overdensities. And as you go down to redshift 0.1, it turns out that what you're actually probing is roughly circumgalactic gas. So the Lyman-alpha forest at low redshift is not anymore a probe of cosmology. It is a probe of circumgalactic neutral hydrogen of things that are happening within a galaxy. And so it is affected by AGN feedback, and it is affected by supernovae. And this has been known for a long time. There was a paper in like 1997 where Ramil Devey does this. But because no one was able to observe it for many years, I think we all kind of forgot about this. But it turns out to be the case. Okay, one interesting thing about this is that because we are now sensitive to the AGN feedback, the Lyman-alpha forest, of all things, has now become a probe, a sensitive probe of what has happened to how AGN feedback is affecting the distribution of gas around halos. So you can change this particular parameter is called in illustrious the strength of the radio mode. What this actually means is the overall strength of the AGN feedback. There is one part of the AGN feedback model that suppresses star formation. A stronger number suppresses star formation more, and a weaker number suppresses star formation less. And you can see that this is kind of, the amplitude of this is kind of controlled by the radio mode. So this is a nice independent check on how the AGN feedback model is working. You've tuned it to match the star formation rate. You have not tuned it to match the neutral gas fraction in the Lyman-alpha forest. So that's one thing. One other thing that you might be noticing about this plot is that although it agrees down here, where I said that there was this underproduction crisis, it does not agree very well over here at higher column densities. So this is interesting. I've zoomed in a little bit here and pointed this out. We're maybe a factor of 5 or maybe even a little more discrepant at this high column density, and we're not quite getting the shape right. So why is this? I do not know why this is. It doesn't. The effect of the feedback model seems to go away at these kinds of high column densities. One possibility, of course, is that increasing the number of photons moves this down. Decreasing the number of photons will move this up. So maybe we can improve this by removing the photons. So instead of a discrepancy we had where we had not enough photons, we now have a discrepancy where there are too many photons. Hey. Another possibility is just that the AGN feedback model in illustrious is way too aggressive, that we're moving too many things out of the high density halos. And this is just removing high columns. This is pulling away too many Lyman limit systems. There should be some that are stuck back in. And this is, this could even be some kind of a numerical effect, right? If you have a blob of gas and you hit it with some energy and that blob of gas is not very well resolved, it will be much more easily disrupted than if it is properly resolved. So But yeah, the moral of this part of the talk is that there is indeed a legitimate problem matching the low redshift Lyman-alpha forest. You can match it with by messing around with your photon density, but if you want to use low redshift Lyman-alpha forest as a measurement of how many UV photons you need, you also have to care about AGM. And that is all. Any questions on this? I was expecting to get more questions on this, but I guess Juno is not here, so okay. All right. So yeah, I did that about right. Okay, so the third thing so this is something I've done more recently, and this is something that has nothing to do with simulations, really. This is a pure observational data science thing. We were trying to find DLAs in SDSS spectra. So DLAs are damp Lyman-alpha absorbers. They are extremely large neutral hydrogen absorbers. They are from neutral self-shielded gas. They have this broadened profile with this damping wing. The natural Lorentzian broadening from the quantum uncertainty in the levels of the hydrogen atom, which I am, again, certain that everyone here has heard of many times. But just in case someone was sleeping through their lecture, I'm going to mention it anyway. There's a well-understood profile that drops off relatively slowly, i.e. slower than a Gaussian, from the center of the line, a saturated core and this damping wing, which makes them easy to tell apart from other absorbers. So in a decent spectrum, in a spectrum with high resolution and low noise, it's very easy to detect these things. The way you do it is by visual inspection. So let us try this. Okay, so this is a quasar spectrum from SDSS. I have helpfully drawn on for you something that approximates the continuum, and I want you all to pick out where the DLA is by visual inspection. This is going to work really, really well because of where I am. Sometimes I give this talk and it doesn't work at all well. Okay, everyone ready? There it is. Who got it right? All of you. Okay. Okay. Yeah, this is a good test of how many people here are observers. So this is something that is reasonably easy for a human to do, right? You can be well-trained. A well-trained human can do this quite well. It took you, maybe a couple seconds to do this in one spectrum. So now you have to do this to 10 to the 5 to 10 to the 7 spectra, which is how many spectra there are in SDSS. This was done for one of the earlier SDSS DR releases, I think by Isabelle Paris from France. And she became unhappy at having to look at all these quasar spectra and has decided not to do it anymore. And as the number of quasar spectra increases, this becomes very clearly impractical, right? For
it takes me looking at one to know I don't. I don't have to wait to 10 to the 6.
How do you know that that's right? You fake it?
How do I know that there's a DLA here?
Yeah. And not 5 of them.
Oh.
Over there.
So I am assuming that the ground truth human observer is always correct in all of this. If you're asking how do I know, are you asking how do I know that the visual inspection got the right answer in this particular case?
The damping one looks very convincing, but it's actually based on, you could imagine that there were smaller lines that actually made it in this case.
So I should admit that in order to make this exercise a little harder, I have chosen a somewhat marginal detection here. So generally, it's more clear.
Marginal by what criteria?
Marginal by well, okay. So one. That is an excellent point, because one problem with visual inspection is that you don't get a significance on your detection. Right? I mean, especially it's going to vary depending on how tired the person doing the visual inspection is, just a little bit. And there'll be obvious things that you miss because you happen to be looking at them at the wrong time. And there'll be things that are kind of not really clear that you notice because before them you happen to see a few spectra that...
I believe you if you said you simulated the spectrum and you put one in, and there it is, and observers found it.
Why not let them get to the machine learning part?
That is not something that I did here, right? So the whole thing so one of the good things about doing this with machine learning is that you do get a principal probability that something is or is not a DLA. And that is a huge bonus. Apart from the fact that just you do not want to expect every single DAISY spectrum to see if there's a DLA in it.
Doesn't this have Lyman beta marked, and so probably the other things that...
Yes, this is Lyman beta.
DLAs, the vital thing that matches up?
That also helps quite a lot, right? Like the other things that look like this guy, I think, does not have Lyman beta in the right place. I think it's here. This guy could, I think, be a low redshift DLA, but it doesn't have a damping wing. I think the thing that convinces you is that this has it. But as I said, the machine learning code actually gives a probability of about, like, I think it might be 50 to 60% that this is a DLA. So it's not, it's by no means sure. And I did that deliberately, exactly because, you know, otherwise people say, well, what's the big problem? I can obviously see this is a DLA. Okay, so how do we do this? So the good thing about DLAs is that we have a physical model for DLAs. We know what a DLA should look like. It's this Voigt profile. The difficult thing with DLAs is that we don't know what the quasar looks like, actually. And the especially difficult thing about SDSS spectra is that they are extremely noisy. You know, the signal to noise is about 1. So this makes it hard. This defeats the easy kind of optimization methods that you would be tempted to use if you had better quality spectra or if you had a galaxy spectrum. And it particularly defeats template matching. So there are papers done where people have looked for DLAs in SDSS spectra using template matching. And they do get catalogs. If you actually try and use this catalog for anything, you have to throw away all of the spectra that have a signal to noise lower than about 4 or 5 because it finds way too many false positives because it just fits to noise. So we taught a computer to do this. This is what, doing repetitive tasks, looking at things 10 to the 5 times, this is what computers are for, right? We invented them purely to spare us this kinds of thing. Because we understand DLAs and we don't understand the quasar, what the machine learning thing is doing here, that the trick for the machine learning code is to learn a model for the quasar and not a model for the DLAs. So it might be tempting if you're more familiar to applying machine learning to working things out in exoplanets or galaxy spectra. It might be tempting to learn a model for the thing you're trying to detect. This is not what we did. What we did was we learned a model for the quasar and then added in our known model for the DLA and used Bayesian model selection to decide whether or not it's there. The model for the quasar that we chose in practice is a Gaussian process. So this is, I think of this, who here has seen these things before? Yeah, about, okay, 50%. Okay, so I do have to tell you what they are, but I'll bore half of you. So these guys, I think of these guys as kind of Bayesian function interpolation. So what you are doing here is you have, this slide hasn't come out as well as it should have, but there should be a gray band around 2 and -2, which mark the 95% contours of the Gaussian process. The Gaussian process assumes that each functional point is well determined, and the value of the function between these two varies depending on some probability distribution, which is conditional on the input set, and conditional on some correlation length for function values between each actual measurement. So more or less what you would do here is you would write down, the way you would derive this is you would write down, hey, assuming I know these things about a function, what is the probability that the function would have a given value in between these two measurements? And once you do that, the Gaussian process sort of drops out. One thing, what I have told you is not a legitimate thing to say. What I have told you is kind of like saying, oh yeah, we interpolate this function using linear algebra. We use a polynomial. The question is, which polynomial do you use? In the case of Gaussian processes, the way you turn this from being a sort of general framework into something that's actually useful is this thing called a kernel function. So the kernel function describes how well neighboring positions in function space are correlated and with which values of with which observations they're most correlated. So in this particular example, they've chosen a kernel such that there's a correlation length of about this, if you can see it here, correlation length of about this. Between these function values. So it's very well determined within one correlation length and then much less well determined, and it gets closer to this guy and it's much better determined. it is not necessary to choose this particular correlation function. In particular, you are allowed to choose a kernel function such that there are strong nonlinear correlations, non-local correlations, between the function values. So you could have the value here being very strongly conditioned, for example, on this measurement. And this is the case in quasars, because quasars exhibit very strong non-local emission lines. So, for example, this is a quasar. This is, I think, this is the mean, the SDSS mean quasar continuum. And this is a realization, I think, using artificial noise. There is an O3 peak here. The position of this O3 peak is going to be reasonably well correlated with Lyman-alpha. There's no way that you're going to get this unless you have a kernel function which has strong non-local correlations. Okay? None of the standard off-the-shelf Gaussian process kernel functions do this. So what we had to do is we had to learn our own correlation function by taking all the SDSS quasars and throwing them through some optimizer. So we use a bespoke learned kernel function with a whole bunch of free parameters. So what this is the covariance, the correlation between each pixel. There are about 10 to the 3 pixels in an SDSS quasar spectrum. So we have a kernel function that is 10 to the 3 by 10 to the 3. This is too many, so we cheat. We use a lower rank decomposition with a PCA. And we end up with 20-odd free parameters. And then all we have to do is compute a 20 by 20 matrix inverse every time we do the optimization. This is what we get. This is our final kernel function. You can see there's high degrees of correlation along the diagonal, which is what you would expect. That's good. There are also high correlations here, this one here, and this one here, between the Lyman-alpha line and this thing here, which I think is oxygen 3. There are other correlations here that it's picking out. Other interesting things that those of you who work on quasars probably know substantially better than I do. I'm showing this here so that if you do work very well on quasar, if you work a lot on quasars and you can read these things by eye and you can tell me if this is right or wrong, now is your opportunity to do so. Yeah.
I'm not going to ask that. Maybe it's related actually. Do you find that you have a better behaved kernel when it's in log wavelength or wavelength?
Wavelength. So we're using the rest frame wavelength here. We found that pretty much any transformation you would do to the data, maybe you think, oh, if I do this little thing, it'll make it easier. Everything we did like that made it substantially worse. Like the thing that we're basically just throwing everything at it. In particular, one thing that really screws you up is you might think, oh, I'll take the obviously crappy quasars and I'll throw them away. If you do that, it starts finding DLAs absolutely everywhere. Because it severely underestimates the amount of noise. Like you really need all the quasars, especially the ones that in principle contain no information.
When you say it underestimates the amount of noise, do you mean really that it's underestimating the true intrinsic variance in quasar spectra? What do you mean by noise in that?
What I meant was that it was underestimating the underestimating the intrinsic variance arising from SDSS's pipeline. So one of the things that hang on, this is the next slide. Okay. So there are two other ingredients than the kernel function. The first is Gaussian noise using the SDSS quasar pipeline, right? And this is the model of the flux within the quasar west frame. The other thing that it causes noise is the Lyman-alpha forest. From the perspective of DLAs, this is a huge source of noise. We have this model for the Lyman-alpha forest where each absorber is an independent Gaussian. So the optical depth of the absorber is a Gaussian, and then the flux is e to the minus optical depth. And this is happening. The continuum model is in the rest frame of the quasar. The Lyman-alpha model is not in the rest frame of the quasar. So they do not add linearly together. So one of the things that I suspect that it is underestimating substantially if you throw away the noisy bits is this Lyman-alpha forest noise. Or it is misestimating which part of the noise goes in which place.
But it's asymmetric with respect to the
Sorry?
continuum. The Gaussian noise is symmetric.
Yes, and this is not symmetric.
Not symmetric.
Right.
Surely you know that or put it in.
But even so, it seemed to confuse the machine learning model if we threw away the low signal to noise things. I don't know why this is. but it happened. One thing to note is that it is not physical to assume that each Lyman-alpha absorber is independent. Right? There are correlations in the Lyman-alpha forest. So for this reason, we don't really have a physical model of the Lyman-alpha forest in this. And because we don't have, what we are estimating is a model of the quasar for continuum plus Lyman-alpha forest absorption. We have a good estimate of the sum of those two. We don't have a good estimate of any individual part of those two. We don't have a really good continuum model, and we don't have a really good Lyman-alpha forest model, because this is not really physical. And it might be that part of why this screwed up if we threw away the noisy quasars was that this, that came back to bite us.
So
Yeah.
is this summary correct? You end up modeling just the average flux received by SDSS along quasar sidelines.
We end up modeling the average flux plus the average variance, the pixel per pixel variance. So what we're looking for, what we're trying to do is we're trying to compute, given a quasar spectrum, what is the probability that it is like a quasar spectrum that you would expect from SDSS?
Right.
Okay?
Right.
And then
So you find the PDF of the average PDF as a function of lambda that
Yep.
SDSS should be sampling from.
That's right.
Okay.
That's what we're doing.
But you also have some variance over some length scale, so that over which you can get your significance of a broad feature of the DLA.
Right.
So the covariance matrix.
So hang on, okay, so this is the slide that comes with that. So what we then do is we add a DLA to this spectrum, and then we have two models. One model has a DLA in it with the parameters of the DLA, the column density and the redshift. The other model has no DLA, and we use Bayesian model selection to say which of these two models is better. So if you underestimate the variance of the flux in SDSS quasar spectra, you're going to get too many DLAs, because anything that doesn't look like the quasar spectra, you're going to think is a DLA. So this came back to bite us a couple of times in the middle, because if there are things in your quasar spectrum that are uncommon features in SDSS quasar spectra but aren't actually DLAs, the optimizer doesn't know that, right? It doesn't have a third option for something else that I didn't tell you about. It has two options. It can be a DLA or not a DLA. So in particular, if there is a broad absorption line in this quasar spectrum, it will think that is a DLA. So we're needing to use a BAL cleaned catalog. The other thing that happens is if you throw it something that is a Lyman limit system past the Lyman limit, which is completely absorbed past the Lyman limit, you are going to get, it's going to think that's a DLA too. Like, there's so much absorption there. What else could it be? It's completely implausible that is not a DLA. So in order to get around this, we cut it at the rest frame Lyman limit. I went back and forth a bit. Yeah, okay. We needed a training sample. Our training sample was the visually inspected survey, including DLAs, with DLAs removed, which is SDSS DR9. So the nice thing about learning a model for the quasar spectrum is that if there are a couple of DLAs that weren't removed properly, this won't make a difference too much, because they'll be sufficiently rare that they won't change the variance that much, and all they'll do is increase it a little bit, and they'll just make us a little bit less certain of our DLA detections. Because this is the same instrument, you have the same selection effects and the same noise pipeline. This is important. I suspect that if you take this model and apply it as is to something with a different noise pipeline, it won't work very well. Right, so this is an ROC curve. This is the true and false positive rate when applied to the training set. Most misses, you can check the misses if you want to look up here and check the things that you are finding that are not in the training set. Most of them actually do look like DLAs the training set just missed. So that's nice. I do show this plot for another reason, which is that when I show this plot to a machine learning crowd, they all say, wow, that's a really great ROC plot. That looks amazing. Yeah, I've never seen an ROC plot that good. But the thing is, when we first did this, when we had a whole bunch of DLA detections that were really Lyman limit systems, the ROC plot still looked really, really good, and it wasn't working at all. So, the moral of this is that I don't really trust ROC plots anymore as a method of telling whether or not your machine learning algorithm is working, because this was great from the start, even when it was rubbish. One of the nice things is that we now get principled errors for each DLA, right? We can say this is a DLA with probability 0.9, this is a DLA with probability 0.8, this is a DLA with probability 0.3. You can take all these 0.3 probability DLAs and multiply them together, and you can get a good measurement of how many DLAs are in each redshift bin, which you couldn't do with visual inspection. So this is the line density of DLAs as a function of redshift. These error bars here are Poisson error bars. These guys, which are based on template matching, do not have error bars. The reason they do not have error bars, I asked him, and he said, because I would not trust them, because I have absolutely no idea how my selection is working. So we do have error bars. So that's good. And even better, we agree reasonably well with both of the earlier measurements, which is also nice. I mean, we're actually kind of midway between the two measurements here that disagree by more than error bars.
Nice. It means you did all this for nothing.
Well,
High redshift.
except for a high redshift. Although a high redshift, the error bars are a little bit large. Yeah. And you notice it has this weird kink in it. I would remind you that the error bars here are highly correlated. Right, so this weird kink is almost certainly just statistical fluctuations, really. Right. And if you think there's a correlation length of maybe 0.4 in Z, you can see this is one bin and this is another bin. They differ by about 1 sigma, which is what you'd expect. But this was nice. This plot I show because it took me a long time to get it. The DLA line density is independent of the signal to noise. So I've not when training, but when computing the DLA populations, I've thrown away all the quasars with a signal to noise less than 2 and less than 4, and I'm getting roughly the same DLA line density. So that means that I'm not finding, unlike template methods, I'm not finding more DLAs in low signal to noise spectra, which is great. The low signal to noise spectra are not providing a lot of information, which is what you would expect, which is what you would hope for.
They may be providing more, it's just they have lower probability. So that's scaling together in a way that you expect based on information.
Right,
But,
yeah.
But isn't this a statement on the redshift dependence of the quasar luminosity function?
What do you mean?
Because the signal to noise is just, I suppose no.
No, because and also because the presence of a DLA is, you still get a DLA at redshift 2 if your quasar is a redshift 5, right? Because you can still measure Lyman-alpha flux, super redwood. This is the total density of neutral hydrogen, omega DLA, and we have measured this also. The reason I like this is that it shows that our high redshift measurements are not tremendously off because they agree reasonably well with a survey from much better quality spectra. So that's kind of nice. Here we agree much better with the DR9 results than the DR5 results. There's a reasonable explanation for this. It's just that these are from an earlier SDSS release, which was too small to get the high com density systems. It just didn't contain any. So it was systematically biased low. Yeah, OK. I have shown you the good things about this, right? The good things about this are that we get high redshift reasonably well, we get error bars, everything is great. I'm now going to show you the bad things about this. So the first thing is that there is some correlation between the presence of a DLA and the redshift of the quasar. So what I've done here is I've shown you the DLA line density as a function of quasar redshift. And of course, you can't see DLAs at a higher redshift than the quasar, which is why there's a cutoff right here. This cutoff is because this is the Lyman limit for the quasar, which we're throwing away everything bluewood of, the rest frame Lyman limit. One thing is that you notice there are somewhat fewer DLAs in low redshift quasars. So this is a little bit weird. Right? You would not expect a DLA at redshift 2 to be necessarily correlated with a quasar at redshift 2.4. Where this is coming from is that there are fewer DLAs near the quasar within redshift of 0.2. So I could have cleaned this. I could have just thrown away all the spectrum near the quasar, and then this null check would have looked fine. I did not do this on the off chance that it was something physical, that there are actually fewer DLAs nearer the quasar for some reason that has to do with galaxy formation. I don't know what that reason is, but yeah, sorry.
I'm sort of curious you did your training basically on the full sample, yes?
Mhm.
So you didn't do the retraining in these redshift slices so that the mean quasar spectrum intrinsic quasar spectrum could potentially come out different in the redshift bins.
No, I didn't do that. I allowed the Lyman-alpha forest absorption to be different in different redshift bins, but I didn't do that with the quasar spectrum. You're right. So yes,
Suppose
if
they
there was
could
some...
trade it off from each other, I wouldn't necessarily expect you to get a different answer if you... But
Yeah, so you're suggesting that the quasar continuum could be redshift dependent, and that would be, yes, that would work actually. That would explain this.
But it's not the case that the forest density explains this, which we do know varies with redshift.
It's not the case that this explains. I think actually we put in the redshift variation of the forest density in response to a referee comment. I think it actually made this a little bit stronger. I don't know why that is. The other issue, which I find kind of interesting, we have a hard cut that there is only one DLA per spectrum. So DLAs are rare enough that this is okay. The probability of them being 2 in a spectrum is sufficiently low that this isn't going to bias our population very much. If you do allow more than one DLA per spectrum, it almost always finds that a given spectrum has either 0 or 2 DLAs in it. So what it will do is it will find the most probable DLA, and it'll say, okay, this is great, and either it will split it into 2 and say, okay, we can get a better fit by assuming there are 2 DLAs that are just really close to each other. We got rid of that by enforcing the DLAs had to be separated by a certain amount. And that's just a classic overfit, right? If you have 4 parameters to fit a given spectrum, you're going to do better. And then what it does is it will find something that looks a little bit like a DLA. It will say that it's a DLA, it'll say that the first DLA is this one, and then make the second DLA this one. So this one will be a DLA with some reasonably low probability, and then this one will be a DLA with some very high probability. So it will never allow us to have one DLA. I don't know why this is. I would love to know. This was my leading order problem with this entire project when we published it, and I don't know the answer to it. So any suggestions welcome.
You said that you did
Yeah.
you got Bayesian decision-making to figure out what your best model is?
Yeah.
Usually, impose a penalty for making the model more complicated. Tuning that up in some way?
Yes, to train up the, that's a good idea.
The model is not as complicated, the world might be that way.
Yeah, well, then we're stuck. Yeah.
Penalizing it for having 2 when it does have 2?
Yeah, but the statistical probability of having 2 is low.
Well, that's a prior.
Which is a prior that we know, essentially, from the, or not know with high confidence, but know to some degree based off of, there's higher resolution, higher signal noise observations that give you a prior on the number of DLAs with a large error bar, and he's refining that measurement.
But they're also clustered. That's the other thing. You'd need to know the clustering to know the...
It depends on what velocity difference you're defining them. They can be clustered on small velocity scales, but on large velocity scales,
It shouldn't be.
yeah, you've already imposed a wide separation. So.
Yeah. So yeah, we should probably pry this away. But knowing what prior actually to do, I'm not sure. If you use the standard, there are standard criteria you can use to penalize more complex models, right? Like the Bayesian evidence or the information criteria. Those are basically ineffective because they're not strong enough. You get an exponentially better fit by adding an extra DLA, usually, and you have a linear penalty by adding the information criterion because it's only 2 extra parameters. So that doesn't work. You could learn a prior for the second DLA that I hadn't thought of. Yeah, we should talk about that. Okay, so to conclude, right, so this is a machine learning technique for detecting DLAs. It gives you a posterior probability for the DLA. We trained it on DR9, we ran it on DR12, we will run it on DR14, we will run it on DAISY, so we're able to scale better and better to the future surveys. We will probably retrain using our, when we do DR14, we will retrain using our catalog for DR12 and then apply it to DR14 rather than using the DR9 catalog. It's completely automatic, which is great because no one has to sit around looking at quasar spectra anymore. we get to use, well, maybe you have to a little bit already, you know. We can use all the data even with the very low signal-to-noise spectra. You can adjust the catalog purity versus the completeness. So if you're interested in something which cannot have any DLAs in it whatsoever, you can remove everything with DLA probability less than, like, you know, greater than 0.2. If you're interested in something that has to contain all the DLAs and you don't really care if there's contaminant, you do it the other way. One other thing is that we have a model for the quasar, right? So this technique should be generalizable to detect other things in quasar spectra, for example, broad absorption lines, or anything else that you might be interested in. And this is something that we're actively working on. So that is all. I've gone horribly over time, so thank you very much.
Could you say a little bit more about why the template fitting couldn't be fine-tuned to actually work?
I mean, maybe you.
What is it about it? It's just too noise sensitive.
It's just the spectra are just way too noisy. I mean, you're almost always going to end up with something that looks like a DLA enough that it fools your template matching, even with a really noisy spectra. You're making a face like you think this is possible. Well, you're welcome to try it. Certainly, no one had done it successfully.
I mean, the other problem is that you have correlated Lyman-alpha absorbers that have column densities significantly below this, like 6 orders of magnitude below this, that can add together because of kinematics to look like something that looks kind of like a DLA, except for the void profile wing. And the void profile wing is in the noise of the spectrum. So it actually is enormously challenging.
So the thing is that the key feature is the wing, and that's just noisy. Yeah.
But that's true of all of your detectors.
Well, but your template doesn't know that the spectrum, you know, a dip here could have different DLA properties than a dip here, right? Because the template does not know where in the spectrum it lives. The key feature with this thing is that it knows where in the rest wavelength, the rest frame wavelength of the quasar it is in the quasar continuum model. Like, it knows that, and your template can't know that. It's phased, yeah.
What are the, sorry.
But if you're welcome to try, yeah.
When you say templates, you mean you take a quasar template and then you just add DLAs to it along with sort of the rest thing below. But you couldn't just take those quasar levels and use that instead of the Gaussian clusters? Because it's in principle then exactly the same thing, because if your template library encompasses all the variation of the quasar.
I mean, that is kind of what we're doing, I guess, right? I mean, if you just take the quasar mean, you'll get fooled because you don't know about the variation, which is, again, wavelength dependent. I guess if you took a whole bunch of banks of intrinsic quasar, if you had a large bank of quasar continuum, yes, you could do that, but I think it would be hard to get enough decent quasar continua at high enough resolution to do this really well. I think the advantage of this is that you can do it, you know, with a noisy, crappy spectrum. I guess if you had a whole bunch of really good theory models for quasar continua, then you could probably get that down. I don't know that we do, though. If anyone wants to tell me that we do, that would be great.